On our last video over 9-11 mass-to-mass stoichiometry, we saw that if we burn 100 grams of ethanol C2H5OH, we would produce 191.1 grams of carbon dioxide pollution. What we're wanting to find out, though, is how much pollution would burning 100 grams of octane. Oct means 8. Octane is C8. H18, and it's one of the primary hydrocarbons found in gasoline. And in this problem, if we're burning 100 grams of octane, they want to know how many grams of carbon dioxide would be produced. So this is a mass-to-mass problem again. Our given is 100 grams of C8H18. What we're trying to find out is how many grams of CO2 would be produced. So when we look at our stoichiometry chart, we are again working a mass-to-mass problem. Our given mass is 100 grams of octane, C8H18. What we're trying to find is how many grams of carbon dioxide will be produced. This will require 3 steps or 3 conversions. We've got to go mass of octane to moles of octane. That just requires the periodic table. Then we want to go to moles of octane to moles of carbon dioxide. That will require a balanced chemical equation. Stoichiometry is merely using the proportions in chemical equations to solve for all sorts of different things that you can learn about the substances in a chemical equation. In this one, we're wanting to find out how many grams of carbon dioxide will be produced. So we'll use the equation to convert moles of octane to moles of carbon dioxide. Then we will use the periodic table to convert moles of carbon dioxide to mass. It will require 3 separate conversions, which we can string across in one long problem. So the first thing, before we even start the problem, we want to make sure we have a balanced chemical equation. C8H18 is being combusted. That means it's reacting with oxygen. It will produce carbon dioxide and water as a product. This is a pure hydrocarbon, unlike the one we had up here, which was a substituted hydrocarbon. This is ethanol. There's an alcohol. This is burning an alcohol. This does have an oxygen on it. However, down here, this is a pure hydrocarbon. So we can go straight up Hollister on this thing. Hollister Clothing Company's acronym is HCO. It tells us the order of what to balance. We're going to balance the hydrogens first. We've got 18 here, so my first thought is to put a 9 in front of the water. 9 times 2 is 18. However, we cannot have an odd number here because this is a pure hydrocarbon. So we take 9 and double it to 18. 18 times 2 is 36. So we'll need 36 hydrogens. 2 times 18 is 36. That takes care of hydrogen. Now we go on to carbon. 2 times 8 is 16 carbon. So I'll put a 16 in front of this. 16 times 1 is 16. And now we're down to our final element, which is oxygen. 16 times 2 is 32 oxygens, plus 18 times 1. 32 and 18 is 50. So we'll have to put a 25 in front of this. Oxygen, 25 times 2 is 50. We now have our balanced chemical equation. We need that because we're going from grams of octane, 100 grams of octane, to grams of carbon dioxide. And we'll need the chemical equation in order for this to happen. All right, first step, as we see on this page right here. Our first step is to go from 100 grams of octane to moles of octane. That's our first step. To do that, we'll need the periodic table to add up the molar mass of octane. All right, the molar mass of octane. There are 8 moles of carbon, C8. 8 times 12.01 is 9608. There are 18 moles of oxygen, C8H18. 18 times 1.008, or you can use 1.01 there, is 18.144. We add those two up. The molar mass of C8H18 is 114.22. So how do we know then what needs to go where? My given's 100 grams of C8H18. I'm trying to find out how many grams of CO2 that will be produced. There's my question. I've got 1 mole is 114.22. How do I know which one's on top? One way is to look right here. I'm going from mass of what I'm given to moles of what I'm given. It says mole on top, mass on the bottom. So when I look over here then, I need mole on top, mass on the bottom. If you don't have a chart handy, if you know you're given the units grams, then we need grams on the bottom. We use the factor label or dimensional analysis to set these up. Whatever dimension or label is here, it needs to be on here so they cancel out. When we're done, we need grams of CO2 left. That has to be on our final conversion. Grams of CO2 will have to be on top so that we're left with that. So we've got 1 mole over 114.22 grams. Next, I need to take a look at what I need to do for the mole to mole portion. I now have moles of octane C8H18. I need to convert that to moles of CO2. It says put the coefficient from the chemical equation in front of moles, and what I'm finding is on top. I need the coefficient from the balance of chemical equation of what I'm given on the bottom. This blue line is my mole to mole. Here we go. First, I need what the coefficients are. I take a look at the balanced chemical equation. It's 2 moles of octane for 16 moles of CO2. 2 moles to 16. I can put this one on top with that on the bottom, or I can put the 2 on top with the 16 on the bottom. I don't want to reduce those to 8 and 1. I want to leave the actual coefficients from the equation in there. Now, how do I know which one to pick? Well, we just saw on this paper here, the moles of the one you're trying to find is on top. Which one are we trying to find? CO2. So the moles of the CO2 need to be on top. 16 moles of CO2. The one we're given, moles of octane C8H18, needs to be on the bottom. If you don't have that chart real handy, we have moles of C8H18 here. We want to factor it out, cancel it with moles of C8H18 there. Boom, they cancel out. And we're trying to go to how many moles of, we're now in moles of carbon dioxide. We're now trying to figure out how many grams there are. If you notice, this part of the problem, 4401 over 1, is the same as this one up here, 4401 over 1. Why are they the same? Because we're trying to find the mass of the same thing. Both reactions produce carbon dioxide. So I want to know the mass of the carbon dioxide. Here we go. We already added it up. It's 4401. I put the mass on top, as it says right here. Mass on top, moles on the bottom. If I don't have those charts real handy, I know that moles are here, they have to cancel out, we're left with grams. If we do the math, 100 times 16 times 4401 equals, divided by parentheses 114.22 times 2, parentheses when those are on the bottom. Burning 100 grams of octane produces 308.2 grams of carbon dioxide. That is like double, well, not double, but it is certainly more than the ethanol. So what we learn here is ethanol is a cleaner fuel. Thank you very much for watching. If you have any questions, don't hesitate to fire me an email.